We will continue our discussions on boundary layer theory. But before we do that, I wanted to show you where everything is in the textbook as far as the viscous flow material goes. Depending on the edition of the book that you have, some of the chapters numbers may be different because Anderson, each edition he adds a little bit more material. Therefore, the page numbers and in some cases the chapter numbers may be slightly different. So the basics of viscosity, derivation of Navier-Stokes equations, things like that which we considered earlier are all covered in chapter 15. It's 32 pages long, but you don't need to read it cover to cover. Whenever you have a question on our slides or on my lecture, you may be able to refer to this particular chapter and get some idea of how the material is described in the textbook. We also looked at a few exact solutions, such as the quart flow, which is flow between two flat plates, and we also looked at Poisson flow, which is flow through a pipe. So quart flow is covered here in chapter 16 of our textbook. We will address the compressible quart flow a little bit later in our course. Recently we've been talking about the boundary layer equations, how Prandtl simplified the Navier-Stokes equations to arrive at a simplified set of boundary layer equations. And we also talked about the boundary layer properties, such as displacement thickness, boundary layer thickness, momentum thickness, shape factor, and shear stress, and skin friction coefficient. So all those concepts are covered in this chapter 17. So after you watch a video, it'll be helpful if you go back and look at the book and read through the relevant sections. It'll help you understand the concepts better. Now we are going to briefly talk about an exact solution or a numerical solution to flow over a flat plate that Blasius did. It's an incompressible flow, and it's not very intricate mathematically, but there are a lot of mathematical steps. We will not treat this as a mathematical problem. We will treat it as how he did it. We will describe it. Then we will jump to the results of his analysis and then use that in our homework and some worked out examples. So this is where the material is, the laminar boundary layer, boundary layer equation derivation and the properties. Navier-Stokes equations are in chapter 15 and 16. Okay, returning back to our theory of boundary layer theory, we talked about Prandtl's boundary layer equations. We went through an order of magnitude analysis. You may recall that we said that there are two length scales. One is the length is in this direction, which is L. The other length scale is in the vertical direction, roughly across the boundary layer. That length scale is delta. Delta is very small compared to L. So we used an order of magnitude analysis where basically if somebody gives us a derivative, we take it, the order of magnitude of the derivative is the maximum value of the function and the distance over which the function changes, in this case from 0 to that maximum value. So this is just a guesstimate to estimate the order of magnitude of a term to see whether we can keep it or drop it. So we went through this process step by step. For example, in the boundary layer, if somebody asks you to find du dy, order of magnitude would be v goes from 0 to u over a distance of 0 to delta. So du dy is of the order of v over delta. That's it. Delta is the boundary layer thickness. V is the edge velocity at the edge of the boundary layer. So normally we'll have some potential flow outside or inviscid flow. So we solve the inviscid flow first, get this velocity information, then solve the boundary layer equations to get this profile. And very often we are really interested in not the details of the profile, but some bulk quantities such as the boundary layer thickness, momentum thickness, shape factor, and also the skin friction. So we went over the order of magnitude analysis. We found that conservation of mass stays the same. It does not get dropped. But we do get some useful information. Both terms are kept. But by looking at this information, if we take the delta to the other side and capital V to the other side, then V over capital V is of order of delta over L. So we got that expression here. So since delta is very small compared to L, the vertical component of velocity in the boundary layer is very small compared to horizontal component of velocity. In the momentum equation, likewise, when we do term by term, we showed in our previous lecture that this term drops out, all the other terms remain. Mu over rho is called kinematic viscosity. So after we went through the order of magnitude analysis, we get this information. Furthermore, all the terms on the left side of order V squared over L, on the right hand side they are of the order of nu times V over delta squared. So if you group delta squared over L squared, then you get 1 over Reynolds number, where the Reynolds number is density times velocity times capital L divided by molecular viscosity. So rho times capital V times capital L divided by mu is Reynolds number. Rho over mu is nu in the denominator. So this is a kinematic viscosity. So this is the Reynolds number. So boundary layer thickness is 1 over square root of Reynolds number of the order. So if the Reynolds number is of the order of 1,000,000, then delta over L is of order of 1 over 1,000. Now for insects, for tiny bugs, Reynolds number will be of the order of 10. For large-scale insects, like the ones you find in South Georgia or in Florida when you're driving through, the Reynolds number may be of the order of 1,000. For birds, Reynolds number may be of the order of 100,000. For airplanes and helicopters, the Reynolds number will be of the order of 1,000,000. For jumbo jet type of an aircraft, the Reynolds number is of the order of 10 million. So the Reynolds number varies widely depending on the length or the size of the geometry, how fast we are flying, and of course the viscosity. In this case, the kinematic viscosity nu, which is mu over rho. Then we talked about V momentum equation. We said everything drops out. The primary information we extract is that the pressure does not change across the boundary layer. So once you find the pressure outside the boundary layer from the inviscid flow, vertically from the edge of the boundary layer all the way to the wall, you can assume pressure is not changing. So this is the governing equation. We also pointed out that this is first order in X. That means you can start with some initial solution and march in the X direction. You don't need two boundary conditions, one in the front, one at the back. We just need a starting point. In the Y direction, though, it's a second order. That means you need to specify the boundary conditions at the wall and boundary conditions at the edge of the boundary layer. You need two boundary conditions in the Y direction. So these are the order of magnitude equations that we developed. We said the most important quantities for engineers are how thick is the boundary layer. So whenever the velocity reaches 99% of the, it's not 0.99%, it's 0.99, then we have reached the edge of the boundary layer. Momentum thickness is, displacement thickness is a measure of the mass flow loss. As a result of it, because we are flowing slowly, as a result of it, the streamlines have to open up or get displaced away from the wall, increase the area so that you can pump the same mass through. So this is the velocity deficit times density is the mass flow rate deficit. to account for it, the boundary layer has to display it outwards. So this is called the displacement thickness. Momentum thickness is like displacement thickness, except we are not talking about a measure of the mass loss, but we are talking about the measure of the momentum loss. So this is the mass flow rate. If the velocity was ue, it will be rho u, ue, dy, ue. Therefore,